So now that you know what simple harmonic motion is, let us now consider some examples of simple harmonic motion. Let us start with a simple pendulum. Now, the name might suggest to you that the motion of a simple pendulum is always simple harmonic, but actually this is not the case. The motion of a simple pendulum can be considered a simple harmonic motion after applying some approximations, okay? So let us now find out what those conditions are and how those approximations lead to simple harmonic motion. Let us consider an ideal simple pendulum. Let's say from some support like this, a pendulum is by a rigid rod. Okay, so let's draw our rod here. So this is a rod, okay. Now the rod can move about this joint, and for simplicity we are going to consider that this rod is massless. So this is a massless rod, okay. Now if we perturb this pendulum a little in this direction, well, you understand that it will go in this circular path, okay. So the new position of the pendulum will be this. Now if we let it go, it will start to oscillate, right? So we'll have some kind of oscillation going on here. But is this oscillation simple harmonic? Well, for that it has to obey Hooke's law, or the differential equation of simple harmonic motion that we discussed earlier. In order to find out the condition for this oscillation to be simple harmonic, we can take two approaches. Either we can analyze the forces acting on these objects, or we can take the energy approach, okay. I think you are familiar with balancing the forces, right? What are the forces acting on this pendulum, and then if you balance the forces, you can find out the force acting here on this pendulum which causes this oscillation, right? Then you can show what condition gives us this simple harmonic motion, okay. So I will let it for you to do. Here I will take another approach, that is the energy approach, okay. So let us find out the condition at which this oscillation can be considered a simple harmonic motion by analyzing the energy of this pendulum. For that, let us redraw this diagram in its simple form. So here is the support again. Let's say this is the rod, okay, this is the bob, and let's call the length of this rod small l, okay. Let's say we perturb this rod, so its new position is like this, okay. So this length is again l, right? Now let's say in this new position, the rod is the pendulum is actually at this height, small h, okay. So then this is small h. So if you complete this triangle, you can write down this distance to be L minus h. So this small distance is L minus h, okay, and the total distance is L. Now let's say this angle is theta, okay. Now at this position, what should be the total energy of this pendulum? Well, the total energy is the kinetic energy plus the potential energy, right? Now the potential energy at this point, we can write it down as simply the potential energy U to be equal to mgh at this position, where h is this small height. Now you can write down this potential energy like this if we let the potential energy at this initial point to be equal to 0. So that is, if we let at h equals 0 the potential energy is equal to 0, then we can write down at this position the potential energy to be equal to mgh. Okay, now let us express this h in terms of this angle theta. Now you may ask why we want to express h in terms of this angle theta. Well, that's because if you raise this pendulum high enough, you can see that it goes on in a circular path, right? So this is some kind of circular motion, and we express circular motions in terms of angular quantities, right? Like this angle theta. So let's see what h is in terms of theta and this length L. So from this triangle we can write L minus h over L to be equal to cosine of theta, right? So this gives us, as you can see, h to be equal to L times 1 minus cosine of theta. Okay, so that means we can write down the potential here to be equal to mg L 1 minus cosine of theta. So this is our potential energy. Now what is the kinetic energy? Well, for that we need to find out the velocity of this pendulum. So what should be the velocity of this pendulum? Well, we can actually write it as L times theta dot. Okay, why is this true? Well, this is the relationship between angular velocity and velocity, right? V equal omega. We are used to calling this angular velocity omega. So V equal omega r, the radius. Here L is the radius, so we can write this thing, right? So this means that the kinetic energy K will be equal to half mv squared, that is L squared theta dot squared. So the total energy here would be the sum of the kinetic energy plus the potential energy. Okay, so we can write down total energy E to be equal to potential energy mg L 1 minus cosine of theta plus the kinetic energy half ml squared theta dot squared. Now if we manipulate this equation, we can write it as theta dot squared minus 2g over L cosine of theta equal, all the constant terms will gather here, so we can write this as a constant. Okay, so this is a constant. Now if we solve this equation, we should be able to get theta from this, and that theta will determine what the motion would be over time. Now we'll get theta as our solution, which will be a function of time. But for that we need to solve this equation, but as you can see, this is a complicated looking equation. It's non-linear, and solving this is not an easy task. So finding out the equation of motion for this pendulum for any value of theta is complicated, right? But if we can approximate theta to be very, very small, actually we can find an easy solution. Before that, let us plot this potential against theta. The potential here, as you can see, which is mgl times 1 minus cosine of theta, if we plot that against theta, what should be the graph here? Well, let us evaluate this thing at theta equals 0, theta equals 0 gives you 1, so 1 minus 1, so you will have 0 potential energy. So the potential energy here is 0. At theta equal pi over 2, what do we get? Well, let's say this is pi over 2, this is minus pi over 2, this is minus pi, and this is plus pi. So at pi over 2, we have cos pi over 2 equals 0, so this thing will be mg times L. So at this angle, pi over 2, the potential is mgl. So if this is mgl, the potential will be like this. And at angle minus pi over 2, actually, this is also 0. So we'll have the same thing here as well. At angle plus pi, well, at plus pi, it should give minus 1. So minus 1, it would give plus 1. So we'll have plus 2 here. So we'll have 2 mgl. So if this is 2 mgl, we should have this point here for the potential. And for minus pi as well, we should get 2 mgl as well. Okay, so now if you plot all the points and join them together, the potential would look like something like this. Okay, now as you can see that this potential has a sinusoidal shape, and solving this is not an easy task. But if we approximate the angle to be very, very small, let's say this region, this small region, you can see that the potential nearly looks like a parabola here. Okay, so that means if we take the angle theta to be very, very small, we can approximate this motion as a simple harmonic motion. So now let us see this thing in details by Taylor expanding the potential in terms of theta. Okay, so we can then write down the potential as a function of theta would be equal to u of theta equal 0 plus dd theta of u evaluated at theta equals 0, okay, times theta minus 0. The next term would be 1 over factorial 2 d squared u d theta squared evaluated at theta equals 0 times theta minus 0 squared. Similarly, the next term 1 over 3 factorial d cubed u d theta cubed evaluated at theta equals 0 theta minus 0 cubed, and it will go on. Now let's find out all these constants. Okay, so first, what is u of 0? Well, u of 0 means the pendulum is here at the initial position where theta is equal to 0, and you know we have set the potential here to be equal to 0. So we have set that u of 0 is equal to 0, right? Now, what is this quantity? Well, this is du d theta evaluated at theta equals 0. So the slope of the potential at theta equals 0. Well, how do you evaluate this quantity? Well, you can find this out from this expression, right, of u. So let us differentiate this quantity with respect to theta, which let's write down here. Du d theta will be equal to, you see, we'll have mgl, this constant term, times, this should return you 0, and differentiating minus cosine of theta should give you sine theta, right? So we would have sine theta. Okay, similarly, we can find out this term as well. So what should be d squared u of d theta squared? Well, you have to differentiate this quantity, right? So it should return mgl. Differentiating sine theta should return you cosine of theta. So actually, as you can see, as we have sine theta and cosine theta here, so if we continue to differentiate these things, we should get repetitively one sine, then cosine, then sine, then cosine again, right? So these things should repeat with some minus or plus sign in front. So now let us put these things in this equation. Okay, so here we can write u of theta to be equal to u of 0. We have set that to be equal to 0, so it is 0. Then we have du d theta, right, evaluated at theta equals 0, and at theta equals 0 you see sine 0 is equal to 0, so it should return you 0 as well. Okay, so this should be 0 as well, so these two terms are 0. So for this term, as you can see, if we put theta equals 0 here, well, cosine of 0 returns to 1, so it will be equal to mgl. So let us put that value here again. Half mgl, and here is theta squared plus, then this is the next term, and as you can see, this term, for this term, if we set theta equals 0, it should return us 0, right? Because here we have cosine of theta, and if we differentiate it again, it will give sine theta, and sine 0 equals 0. So the odd terms here, where powers are 1, 3, 5, they will be 0. So it is actually equal to 0. So the next term will contain theta to the power 4. So we can say that we'll have the rest of the terms which will be of the order theta to the power 4. Okay. Now if we apply the approximation that theta is very, very small, we can ignore these terms. Okay, so we can approximate the potential here to be approximately equal to the potential half mg L theta squared. Okay, and this is accurate to the order of theta cubed, because theta cubed was 0, and we ignored the order of theta to the power 4 terms. Okay, so the energy, the total energy, we can write that now to be equal to the potential energy, this thing, half mg L theta squared, plus the kinetic energy, which was half ml squared theta dot squared. Okay, ml squared theta dot squared. Now, as you know, we have the conservation of energy principle, so this thing will remain constant throughout time. So if we differentiate this quantity with respect to time, it should return you 0. So let's do that. Okay, so dE over dt will be equal to half mgl. You are differentiating theta squared with respect to t, so first it will return to theta, then theta dot, okay, the derivative of theta with respect to t, plus half m L squared, and if you differentiate this thing, it should return to theta dot, and again differentiating theta dot, you should get theta double dot. This two will cancel out with this two, this with this L, we can factor it out from this one, so we'll have only L here. Okay, so again we have theta dot here as well, so they will cancel out as well. So all we'll have is here on this side L theta double dot, plus on this side g theta, and this is equal to 0. Now if we rearrange this thing a little, what should we get? Well, theta double dot plus g over L times theta equals 0. Now this equation, if you look a little closely, you'll see, well, this is the differential equation of simple harmonic motion, right? Which was previously x double dot plus omega squared x equals 0. So you see, this is an analogous equation to the simple harmonic equation. The only difference here is we used angular variables. So that is, if we consider theta to be very, very small. Okay, how small? Well, here we consider theta to be very, very smaller than 1. Okay, so then we can approximate the motion of a simple pendulum here as simple harmonic motion, as you can see. And we can easily find out the solution of this equation, which will be surely of the form theta as a function of t will be some constant, let's call that a, times cosine of omega t plus phi. Okay, so this will be the form of theta here, where omega is the angular frequency, and from this equation we can tell that this omega is equal to square root of g over L. So this is how we can approximate the motion of a simple pendulum energy approach. We could have also taken the force approach, okay, by analyzing the force on the pendulum, okay, but I will leave it to you to do it by yourself, okay. So you can also show that for if we analyze the force on it, we can come to this conclusion after applying the approximation that theta is very, very small, okay.